In this section of the book, we're going to deal with a topic that's closely related to finding area in the xy plane. We are going to find area. But area, well, the nicest way to say it is swept out. You imagine some particle or some object moving in the xy plane, and you picture a line segment connecting the origin to the particle or the point that's moving, and you look at the area that's swept out by that line segment as the particle moves, and you keep tracking it. The most famous example of such a thing has to do with one of Kepler's laws of planetary motion, which is one of the exercises on area swept out by a planet as it moves around a star, or one of the planets in our solar system as it moves around the sun. But the main reason we want area swept out is so that we can apply it to areas of regions defined in terms of polar coordinates. And there it is kind of nice to view the area as something swept out as an angle changes. So that's what we're going to do. So what's the problem? So you imagine some particle, some object, some point, something moving in the xy plane. So you have a parametrized curve like we've talked about. So it means you've got x is a function of some parameter t, which I like to think of as time, since I'm thinking of a particle or a point moving in time. And so you've got x of t and y of t, and you form the vector function or the position function that's just the ordered pair x of t, y of t that tells you where the particle or the point is at time t. And so you picture that. So I'm imagining this as part of the path that our particle, I'm going to keep talking about it like it's a particle. You imagine this as part of the path that the particle is moving along, and then we want to know about the area swept out. And what that means is as the particle moves, if you connect its position with the origin by a line segment, and look at kind of how that line moves, look at all the points that line segment moves through as the particle moves, then you get some plane region and it has some area, and that's the area swept out. And so you're here at time t, and you're up here at time t plus h, and I'm using h like we use when we define derivatives, because yes, I'm thinking of h as a very small change in time, because we need to do an estimate, and then we'll think of it in infinitesimal terms and get an infinitesimal amount of area swept out, and then talk about integrating that to get the total area swept out. So here you are, here the particle is at time t, here it is at time t plus h, and we first want to estimate this area. So we estimate it kind of like we do for arc length. You estimate it using a straight line there, and estimate the area swept out as the area of this triangle. So first you have a geometry problem, a high school geometry problem that you need to do. That problem is, suppose you've got a point here, like AB, and you've got a point here, CD, and the question is, in terms of A, B, C, and D, in terms of A, B, C, and D, what's the area of this triangle? We have to do this problem before we can do the calculus problem, the integration that we need to do. And part of what I write is going to use the relative positions of A, B, C, and D as I've got them drawn, but once we put in some absolute values, what we do will work regardless of which is higher, which is lower, which is to the left, which is to the right. It just won't matter what quadrant they're in. So I'm going to do things kind of using this picture, but when we put in absolute values, it'll apply to anything. So we'd like to know how to find the area of this triangle. It's easy. You drop these two perpendiculars, And then the area of this triangle that we're after, well, you take the area of this triangle, you take the area of this triangle plus the area of this parallelogram, and then you subtract the area of this triangle down here, and you'll get the area of the triangle that we're after. So you do this, the area of the triangle is, all right, so we take the area of this triangle, right here. Area of this triangle. Well, this coordinate is A, the x-coordinate of that point. This coordinate is C. So what's the area of this triangle? 1/2 the base times the height. So you get 1/2 A times its height, which is B. You add to that the area of this parallelogram. The area of that parallelogram, 1/2 the sum of the bases times the height. The bases are the parallel sides, so these are the bases. So 1/2 the sum of the bases. So that's this, which is B, plus this, which is D, times its height, which is this distance, which is C minus A. 1/2 the sum of the bases times the height. And then we need to subtract the area of this triangle. And that'll leave us with the area of the triangle that we want. The area of that triangle is 1/2 the base times the height, so 1/2 the base, so minus 1/2 the base, which is C, times its height, which is D. And you do that, and you factor out the half, and you get AB plus, and then you multiply this out, plus a BC minus an AB plus a CD minus an AD, and then minus this CD right here. And what you should see is that the AB cancels with the minus AB, and the CD cancels with the minus CD, and you're left with BC minus AD. So you're left with 1/2 BC minus AD. That, of course, for arbitrary A, B, C, and D, that could be negative, but if you want this formula to be correct, no matter what the relative position of A, B, C, and D is, you put in absolute values, and then, I don't know, just because I like having A first, once I take the absolute value, I could have AD minus BC and take that absolute value, and somehow that sounds better to me, so I'm going to do that. The area of this triangle, 1/2 the absolute value of AD minus BC. Great. That is kind of the high school algebra geometry problem we have to do to get anywhere. So now we come back to the picture we care about. We're here, and so we are at our points, actually have coordinates. Actually, let me erase this picture so that I can have the room. Also, we don't need the picture anymore. Our points were P of t, which is x of t, y of t, and P of t plus h, which would be x of t plus h, y of t plus h. And so what we get is the area of the triangle that goes from the origin and then has one vertex at the origin, one vertex here, and one vertex here. The area of our triangle now is, we use the formula we just developed. It doesn't matter which one you call A, B, and which one you call C, D. It really doesn't, I guess, to make it match with what I had in the picture. This would be the AB, and this would be the CD, but it's 1/2 A times D, so this times this, so x of t plus h times y of t minus BC, so minus y of t plus h times x of t. Great. But we want to kind of pull out the h, because we want to see what happens is when h is an infinitesimal change in t, and somehow we want to end up with, we think of h as dt, an infinitesimal change in t, And we want to get that dt outside of here so that we have dA equals some function of t times dt, and then we can integrate to get the total area swept out. So what do? Well, there are lots of ways to approach it at this point, but maybe the easiest, I think it's the easiest, is to say that, oh, well, x of t plus h minus x of t over h is approximately x prime of t. Of course it is, because the limit of this as h approaches 0 is by definition the derivative x prime at t. So when h is close to 0, this should be a good approximation. Now I am thinking of h as close to 0. I guess I'll write that h close to 0. Multiplying both sides by h and adding x of t, we're going to use that x of t plus h is approximately x of t plus x prime of t times h. And of course we get exactly the same thing with y of t, that y of t plus h is approximately y of t plus y' of t times h. And we expect that approximation to be better as h is smaller, because the limit as h approaches 0 of this is an equality. So what does that mean you get for this area? If you now put this in, it's approximately, and the approximation should get better as h gets smaller. I need to keep saying that because eventually I want to say, and now we let h be infinitesimal. And so you put this in, and this is approximately, all right, so what have we got? We've got the x of t plus h, but that's approximately x of t plus x prime of t times h. So you put that in, and we will get that this is x of t plus x prime of t times h times y of t minus, and then y of t plus h is approximately y of t, I've got a big approximation sign out there, plus y prime of t times h times x of t. Close my absolute value signs. I don't need this anymore, and it's in my way. And when you simplify this, what happens is you get an x of t, y of t, but then there's minus an x of t times y of t, so those cancel. And you get the absolute value of x prime of t times y of t times h, and then minus what we're left with over here, which is y prime of t times x of t times h. And then you can factor out the h. And so what we find is that our area swept out is approximately approximately 1/2 the absolute value of x prime of t times y of t minus y prime of t times x of t times the absolute value of h. So, and that this approximation gets better and better as h gets close, or it gets arbitrarily good as h gets arbitrarily close to 0. So in the end, dA, the infinitesimal amount of area swept out, is equal to 1/2 the absolute value of x prime of t times y of t minus y prime of t times x of t times, well, this h that's becoming the absolute value of h, but we're assuming dt is positive and infinitesimally small, we get this. And this is what we use. The infinitesimal area swept out is this. So the area swept out, and we could use this as the definition, but this is supposed to motivate it. Area swept out between two times is the integral as t goes from some t0 to t1 of the continuous sum of all these infinitesimal areas. So it's the integral from t0 to t1 of 1/2. You differentiate each function once, multiply by the other thing underived, and subtract. Take the absolute value and integrate that. Okay, so that's what you get. You can use this to find area of regions in the plane, except you have to be careful. This is area swept out, and you might run over the same points more than once, and then you don't want to count. If you're trying to count, or if you're trying to calculate area in the plane, you have to make sure that you don't count things more than once. So, for instance, we're going to look at, so here's an example. We're going to look at x of t equals t squared, and y of t is t cubed for t between -1 and 1. Now, you could have a graphing calculator graph this for you, or a computer. It's really not too hard to do by hand. If parametrized curves bother you, if you square y, you get t to the 6th. If you cube x, you get t to the 6th. So the path that this is moving along is y squared equals x cubed. So because this is y squared, the x coordinate's always greater than or equal to 0, but y could be positive or negative. It's not particularly hard to see that it does something vaguely like this. When t is -1, you're at 1 minus 1. So you're down here. So at -1, 1. So here you are at t is -1. When t is 0, you're at 0, 0. So here you are at t equals 0. And at t equals 1, you're at 1, 1. So you're up here at t equals 1. So it's not hard to convince yourself that in this example, what's happening is t goes from -1 to 1 is you start down here, you move up to here, and then you're going over here. So the area swept out, would have been nicer if I had drawn this bigger. The area swept out as you do that is, so you're always connecting the origin to points. The area swept out is this region. These two little curved regions that are curved on one side, straight on the other side. It's kind of clear from symmetry that the area swept out is just that area counted twice. We don't really have to do that. The integral's not any harder to do. So from -1 to 1. So why don't we do this? The area swept out. So what is that area? The area, whether you think of it as swept out now, or whether you think of it as just the area of this orange region, it is the integral as t goes from -1 to 1 of 1/2 the absolute value of, and then you take the derivative of this one, so x prime of t times y of t minus y prime of t, so that's minus 3t squared times x of t dt. This is 2t to the 4th minus 3t to the 4th. That's t to the 4th. Absolute value of t to the 4th is t to the 4th, because it's an even power. You get the integral from -1 to 1 of 1/2 t to the 4th power dt. That is 1/2 times t to the 5th over 5, evaluated from -1 to 1. And that is 1/10 minus -1/10 So 2 times a tenth, also known as a fifth. So we get 1/2 times a fifth minus a fifth. So that's 2/5 times a half, 1/5. So that's the area. It's relatively easy because I picked an easy example. If you made the functions of t difficult, we would have gotten a very difficult integral. The integral that you set up wouldn't be, setting up the integral wouldn't be difficult, but calculating the integral could be just as bad as any integral could ever be, because basically you could pick anything for x of t and y of t. Let me mess with this example just a little bit and then move on to polar coordinates. What would have changed in this example had I, instead of using this parametrized curve, squared both of them? So that this is t to the 4th and this is t to the 6th. And still look what happens between t is -1 and 1. Well, it's still true that if you cube this, you get, and square this, you get equal things, because if you cube this, you get t to the 12th. You square this, you get t to the 12th. Those are equal. So we're still looking at points on the curve y squared equals x cubed. So our points lie on this, but before we had t cubed, and we were looking at some negative t's, and you can cube negative numbers and get negative numbers. But now this is t to the 6th, and that only gives you numbers greater than or equal to 0. So even though t can be negative, y can no longer be negative. We are no longer moving on this bottom part of the curve at all. So what is happening? Now, when t is -1, you're at 1, 1. So when t is -1, you're here. When t is 0, you're here. And when t is 1, you're back up here. It's not hard to convince yourself, you could prove it, but it's not hard to convince yourself that what happens is at -1 you're here, you move into the origin along the curve, y squared equals x cubed, and then as t goes from 0 to 1, you move back out. This means that we count, that the area swept out would count the area twice. Right? So that if we calculate the area swept out between -1 and 1, we're going to get twice this region, which should be a fifth again, because by symmetry we believe that that part of the region that was down here had the same area as this part. We counted each region when we did the earlier integral. Now we'll count this region twice. Or if we actually just wanted the area of this region, we just have to make sure we integrate as t goes from -1 to 0 or 0 to 1, but not both. Because if you do both, you're counting the same points twice, once as t moves down from -1 to 0, and once as t moves back up. So let's calculate the integral from -1 to 1 and see that we get the same thing that we got before, but this time it won't be because we're getting the area of the region. It'll be because we're counting the area of the region twice. It's just that our region now is half of what it was before. It is kind of cool that, we made the functions, well, I don't know, significantly more different. We squared them, and you might think this would have kind of a dramatic effect on the integral, but it better not, or math isn't working today. So let's see how this changes things, but make sure that we get the same final answer. We should. So once again, you take x prime of t, but now it's 4t cubed times y of t. So that's t to the 6th minus y prime of t, 6t to the 5th times x of t, t to the 4th. And so we get, it really is kind of amazing that this is going to come out to be the same. Now we have 9th powers of t. How can this possibly come out to be a fifth again? Well, we'll see. Here's t to the 9th, t to the 9th, 4t to the 9th minus 6t to the 9th. So we get negative 2t to the 9th, but we have absolute values. But now the absolute values are important because we get an odd power of t. T can be negative. And so the absolute value actually has an effect. So let's do this. -1 to 1. 1/2, we get the absolute value of 2t to the 9th. Well, we get 2 times the absolute value of t to the 9th dt. The 2's cancel. Good. But we still have to integrate from -1 to 1 t to the 9th, the absolute value of t to the 9th. But the absolute value of t to the 9th is negative t to the 9th when t is negative, and positive t to the 9th when t is positive. So we get, we need to split up the integral. We'll go from -1 to 0, t to the 9th dt, plus 0 to 1 of the absolute value of t to the 9th dt. And the whole point is, when t is negative, the absolute value of t to the 9th is negative t to the 9th. When t is positive, the absolute value is just t to the 9th. Now you integrate, you get minus t to the 10th over 10, evaluated from -1 to 0, plus t to the 10 over 10, evaluated from 0 to 1. You plug in 0, you get 0. You subtract what you get when t is -1. All right, so we subtract this negative thing. So plus a 10th, plus what you get when t is 1, a 10th, minus what you get at 0, which is 0, we get 2/10, also known as a fifth. The same thing we got before, yippee. It's, math works again. We got what we expected to get. But the calculations along the way look different, and it's really cool that you get the same thing. All right, that's area swept out. To be honest, that's not a topic that a lot of people consider that important in a calculus course. It's cool, and certainly Kepler's laws are cool. But the real reason we want to do this is so that we can look at area of regions defined in terms of polar coordinates. So this will be a quick introduction to polar coordinates, and then we'll do a calculate the area of a couple of regions that are described in terms of polar coordinates. So polar coordinates, it's you are used to x and y coordinates in the plane, so Cartesian coordinates named after Descartes. So a point xy in the plane is said to have polar coordinates r theta So really, I should say a point with Cartesian coordinates xy in the plane is said to have polar coordinates r theta, provided that x equals r cosine of theta and y equals r sine of theta. What this means is that if somebody gives you polar coordinates, r and theta, you can easily produce the Cartesian coordinates. You just take r times cosine of theta to get x, and r times the sine of theta to get y. It is not so easy to go the other way. Given x and y, how do you produce r and theta? Well, here's the good news, bad news. There are an infinite number of choices for r and theta that make this true. First of all, because sine and cosine are periodic, 2 pi periodic, certainly if a point has polar coordinates r theta, it also has polar coordinates r theta plus 2 pi. So that's one thing. Also, you can take negative r's. And so instead of going around 2 pi and saying you get the same thing, you could negate r and only go around pi. And if you negate r both places and then add pi to theta, that also gives you the same x and y. So every point in Cartesian coordinates, every point in the xy plane has an infinite number of sets of polar coordinates. So for instance, let me look at your standard point in Cartesian coordinates at 1, 1. Here we are at xy is 1, 1. Now I feel obligated to write xy is 1, 1 to not confuse. In polar coordinates, well, one set of polar coordinates for this is, well, you let r be this distance from the origin out to the point, and you let theta be this angle. And then you should know that that means that exactly that the x-coordinate is r cosine theta and the y-coordinate is r sine theta. So in this particular example, that would mean r is the square root of 2, and theta is pi over 4. But this is just one set of polar coordinates for that point. As I said, you could also say it's the square root of 2 pi over 4 plus 2 pi. Or you could subtract 2 pi, or you could add 7 times 2 pi, so 14 pi. There are an infinite number of sets of polar coordinates for that point. But you could also negate r and then just go around by pi. So I claim you get the same point. Another pair of polar coordinates for this would be minus the square root of 2 and pi over 4 plus pi. Why? Because when you add pi and take cosine, it negates it. You get negative what you got before. And same thing with sine. If you add pi to theta, it negates it. But then I also negated the r. So this is also polar coordinates. But then you could add integral multiples of 2 pi to this. The way you picture this is for positive r, you picture this r and this theta, and just remember you can always add 2 pi. For negative r's, you think, you shoot through the other side, so the negative r puts you here. So here's, kind of think, negative the square root of 2 for r. I mean, of course, the distance is the square root of 2, but if you're thinking of this point, it's kind of negative. You think of this as the negative direction, and it's in terms of heading that way, this is negative the square root of 2. And then this angle is now this theta, but plus an extra pi. In any case, the point is that you have to be careful with polar coordinates. If you're given polar coordinates, it's easy to get x and y. If you're given x and y, there are an infinite number of pairs of polar coordinates. Also, notice that the origin has even more, a bigger infinity of coordinates. If you're at the origin is r theta equals 0, and then theta can be anything at that point. I'll just write anything, because as soon as r is 0, you're at the origin. So if you try to solve these for r and theta, you can't succeed because there are an infinite number of choices, but there are things you can write. If you square x and you square y, you get r squared cosine squared plus r squared sine squared, and you factor out the r squared, you get r squared times cosine squared plus sine squared. So you quickly conclude x squared plus y squared is r squared. So r has to be plus or minus the square root of x squared plus y squared. Well, yeah, that's what I was just saying, that r is, if it's plus, this is the distance of the point from the origin. If it's minus, it's negative the distance of the point through the origin. You think of it as coming out the opposite side from the positive r. So r is plus or minus this. There are some authors, some texts, some references will tell you, we're only allowing r's that are greater than or equal to 0. That means then you would definitely pick plus and you wouldn't allow any of these negative r's I'm talking about. That's not so nice, because one of the things that's so nice about polar coordinates is it's easy to describe very cool symmetric looking curves in terms of polar coordinates. And one of the reasons that you get some of the symmetries is that you allow these negative r's to mean you've kind of shot through the origin and done this symmetry about the origin by doing that. So I don't want to restrict ourselves to r being greater than or equal to 0. But if we did, then r would have to be positive here. And then you can say, oh, but once I know what r is, as long as it's not 0, so if you take r to be the square root of x squared plus y squared, so you pick the positive one, or the non-negative one, and you're requiring it not to be 0, because if it is 0, you're at the origin, then if you divide both of these equations by r, you get cosine of theta has to be x over r, so x over the square root of x squared plus y squared. And then sine of theta is y over the square root of x squared plus y squared. But that means that this completely, right, you've specified sine of theta and cosine of theta. That means you've completely determined theta for theta between 0 and 2 pi, including 0, not including 2 pi. Knowing sine and cosine, both of them, tells you exactly what theta is between 0 and 2 pi, not including 2 pi, but including 0. And you can get it by using some of the inverse trig functions as long as you pay attention to which quadrant you're in. So for instance, tangent of theta, sine theta over cosine theta, would be y over x. The square roots would cancel. And so you could say theta is the inverse tangent of y over x, provided that inverse tangent gives you back an angle that's in the right quadrant compared to where you know you are, because you know whether this is positive, and this is positive, or this is negative, and this is negative. Okay. The point, what you should be getting out of this is not, oh my God, how do I calculate all these r's and thetas? Yes, you should be able to do it. But the real point is we want to look at some curves that are described in terms of r and theta and see how cool they are with easy equations, and see if we can find area trapped between the origin and those curves. So, for instance, I want to look at so sketch the curve. Given in polar coordinates. By r equals 1 plus the cosine of theta. So we mean that r and theta are specifying polar coordinates of points, and we want to look at the set of points in the plane whose polar coordinates satisfy this equation. Now, cosine of theta is between minus 1 and 1, so 1 plus it is always greater than or equal to 0. So at least these r's are greater than or equal to 0, and so the r is just distance from the origin. And to sketch this, don't plot a bunch of points. Think about what happens. Think about, oh, what happens as when theta goes from 0 to pi over 2. So what happens is theta goes from 0 to pi over 2. When theta is 0, you get the cosine of 0, that's 1. 1 plus 1 is 2, so okay. Yeah, you're at distance 2. So this will be distance 2. So here we are. Theta is 0. And theta now measures the counterclockwise angle you make with the positive x-axis, as I drew in the other picture. So theta is 0. So your angle from the positive x-axis is 0. Theta is 0, r is 2. As your theta increases to pi over 2, what happens? Well, the cosine of pi over 2 is 0. And so, and cosine of theta constantly decreases from 1 to 0 as you do this. So as your angle increases from 0 to pi over 2, your r drops from 2 down to 1 plus 0, down to 1. So here's 1. So as your angle does this, your radius drops. So just kind of sketch that in. Your radius drops as the angle changes. Okay. Fine. Then what happens? What happens when theta is between pi over 2 and pi? Well, as theta goes from pi over 2 to pi, cosine of theta starts at 0 and it drops to minus 1 when theta is pi. But we're adding 1 the whole time. So r, so as your angle goes from here, pi over 2 to pi, your r drops from 1 down to 1 plus minus 1 down to 0. So as your angle does this, your distance from the origin decreases all the way down to 0. So as your angle keeps increasing, your distance from the origin keeps dropping down to 0, which means you're at the origin. Then what happens? As theta goes from pi to 3 pi over 2, cosine of theta increases from minus 1 back to 0, which means r increases from 0 up to 1. So as your angle keeps increasing from pi to 3 pi over 2, your r starts getting bigger. So and it comes back out to r is 1, a distance 1 from the origin, but now at angle 3 pi over 2. So you're down here at minus 1. And then as theta increases from 3 pi over 2 to 2 pi, cosine of theta keeps increasing from 0 to 1, which means 1 plus it goes from 1 to 2 as your angle increases from here to here, and so you come back and close this curve. This thing that looks vaguely heart-shaped is called a cardioid because it looks vaguely heart-shaped. Cardioid. And it's just one of the kind of the cool curves you can get in polar coordinates. As theta keeps increasing, you just go over the same points the whole time. But that's the cardioid. And we could ask for the area inside the cardioid. And what would we use for a parameter? Well, I was using t when I was talking about area swept out. But now we have a clear parameter, theta. We use theta as a parameter. Theta tells us where we are at each point in time. I was saying theta is 0 here, pi over 2 here. Anyway, so as theta increases, you go all the way around the curve, and we need for theta to go around. And if we want the area inside, that would just be the area swept out as theta increases. So we're back in the setting where we were before, except in place of t, we have theta. You might think in r and theta play the roles of x and y in our formula that had x prime of t times y of t minus y prime of t times x of t. No, you have to put in what x and y are. That formula was in Cartesian coordinates. And so we have to figure out what it reduces to in polar coordinates. So let's do that. So x is our cosine of theta, and y is our sine of theta. So this is how you go from polar coordinates to rectangular coordinates, so Cartesian coordinates. But we're talking about, suppose you're given a curve in the form r is given to you as some function of theta. Like we had r is 1 plus cosine of 2 theta. And then we want to use theta for a parameter. Well, that means that as far as x and y are concerned, what we're looking at is x is f of theta cosine of theta, and y is f of theta sine of theta. And now, it doesn't matter that theta is theta, not t, that's fine. But what does matter is we have to use our formula from before. The area swept out as theta goes from some theta 1 to some theta 2, and you want to make sure you if you're trying to find the area of a region, you want to make sure you don't count points more than once, or you could actually count the same ray twice, as long as there are a finite number of places where you do that, because a single ray or a single line segment doesn't add any area. So in fact, we don't mind if we come back around and like count a line segment twice when we kind of close our curve, because it doesn't matter. Line segments don't give us any area. It would only be if there were a whole interval of times where there was overlap that it would be bad. The area swept out. We'll integrate from theta 1 to theta 2, and now we need 1/2 x prime of theta, y of theta, minus y prime of theta, x of theta, d theta. Now, you might go, well, that's going to be awful because of the product rule. In fact, this simplifies greatly. So let me do that. It's kind of amazing how much it simplifies. So x prime of theta, product rule. First thing times the derivative of the second, plus the second thing times the derivative of the first. This y prime of theta, get something analogous. Y prime of theta, first thing times the derivative of the second, and plus the, well, you differentiate this one and leave the first part. All right, this. All right, so x prime y theta. All right, this times this. All right, so what do you get? I guess I'll write this one up here and this one down here. X prime of theta times y. So we get, all right, we'll get f of theta squared. So all right, f squared theta. We get minus sine times minus sine squared theta. And then plus an f theta, f prime of theta, sine of theta, cosine of theta. All I did was I hope, was multiply this times that. I get f theta squared minus sine squared plus f prime. Yes, that looks good. And this, without the minus sign, I'm not, in what I write, I'm not meaning to include the minus sign. We need to do y prime of theta times x of theta, so I need to multiply this times that. And what I get is f of theta squared, so I'll write f squared theta. And then I get a cosine squared theta, and then plus f of theta, cosine of theta, f prime of theta, times sine of theta, cosine of theta again. Okay, so what happens? You have this quantity minus this quantity. The f theta, f prime of theta, sine of theta, cosine of theta cancel, which is nice. And you're left with f squared theta times minus sine squared, and we're subtracting, minus f squared theta cosine squared. If you factor out the f squared, you get f squared times negative sine squared minus cosine squared. That's minus 1. But we're taking absolute values. So all we're left with is the absolute value of f squared, but it's something squared, so it's positive. We don't need the absolute value signs. What we come out with is in polar coordinates, the area swept out by r equals f theta is exactly 1/2 the integral from theta 1 to theta 2 of just f of theta squared, but f of theta is r squared d theta, so this. So yeah, that got a lot simpler. It looks a lot better. It looked like it would be worse than kind of the normal parametrized formula, but in fact, it just got a lot better. You take whatever your function is of theta, you square it, and you integrate. So let's do that for the cardioid. We'll get the cardioid by letting theta go from 0 all the way around to 2 pi. As I'll say it again, That means that we'll count this line segment twice, but just like when you do area under a curve, overlapping line segments, that doesn't add any area. If we let theta go a little bigger, so we were overlapping a region with some area, that would be a problem, but just overlapping one line segment, not a problem. And so, what's the area inside that cardioid? You integrate. Now, I'll say it again. The integrals that you get when you do this kind of thing can kind of be arbitrarily bad. It depends on what f of theta is. This one's not particularly bad, although you do have to remember either an integral formula or integrate by parts or remember a trig substitution. You have to do one of these things, or look it up. Area inside cardioid. That just means that to find it, we'll take 1/2 the integral from 0 to 2 pi of 1 plus the cosine of theta squared d theta. That's all you do. How do you integrate that? Well, there are lots of ways. The most straightforward one is to go ahead and square it, multiply it out, so you get 1 plus 2 cosine of theta plus cosine squared theta d theta. This just integrates to theta. This integrates to 2 sine of theta. This, either you have to do some integration by parts or look up a formula, or you can remember a trig identity. One trig identity for cosine squared is 1 plus the cosine of 2 theta over 2. So instead of integrating cosine squared, you can integrate this. And when you integrate this part, you'll make the trivial substitution u equals 2 theta. So we end up needing to integrate this thing, 1 plus cosine of 2 theta, plus 1 plus the cosine of 2 theta over 2 d theta. And as I've said, you can do that part different ways. I'm going to look at it that way, but it doesn't really matter. And so what I get is 1/2. You get a theta plus a 2 sine theta plus 1/2 times the integral of 1 plus cosine of 2 theta. That will be a theta. And then the integral of cosine of 2 theta, you make the trivial substitution. What you get is it's the sine of 2 theta, but over an extra 2. And all of this is evaluated. All of this is evaluated as theta goes from 0 to 2 pi. So what do we get? You get a 1/2 2 pi. Sine of 2 pi is 0. You get a plus 1/2 of 2 pi plus another 0. Okay, minus what you get when theta is 0. When theta is 0, all of this is 0. So you get this. This is pi, so 3 pi times 1/2, 3 pi over 2, for the area inside the cardioid that we had. Okay, so, that's what you get inside the cardioid. I'd like, just as an example, I'd like to look at one more polar curve described in polar coordinates and calculate area. Not so much because the area calculation is any worse, but because the curve is so much different, even though it looks like you barely change things. So let's do that. So as my next example, I'd like to look at the curve r equals 1 plus the cosine of 3 theta. Now, it really doesn't look like I've changed that much. This is still always greater than or equal to 0, so r will be distance from the origin. All I've done is stuck that 3 in there. How much different could the curve look? Well, we'll see. So what happens? So it's nice to analyze what happens kind of the way we did before when you look at what you're taking sine or cosine or both of, and you look at where that angle is 0 and where it's pi over 2 and where it's pi and where it's 3 pi over 2 and back to where it's 2 pi. But now that means we would look at where 3 theta is 0 and where 3 theta is pi over 2 and where 3 theta is pi. So it goes, it goes like this. What happens is 3 theta goes from 0 to pi over 2. Well, that's the same as i.e. dividing by 3. That's theta is between 0 and pi over 6. So what you're looking at is pi over 6 in degrees. That would be 30 degrees. That's easier for most people to think in terms of. So let me try to draw. Here's 30 degrees. We're going to need 60 degrees. Let me just try to draw in all these 30-degree going up in 30-degree increments. Of course, my ability to sketch these is limited. So what happens? As theta goes from 0 to pi over 6, so as your angle increases from here to here, 3 theta is going from 0 to pi over 2. So cosine it starts at 1 and then drops down to 0. So r goes from 1 plus that, so 1 plus 1. So once again, it starts at 2. And as your angle now goes from 0 to pi over 6, r drops down to 1. So I don't know, 1 looks like it's about there. So a distance of 1 from the origin. So as your angle goes from here to here, your distance from the origin drops from 2 to 1. Does that look about right? So it drops down to there. Great. What happens as 3 theta goes from pi over 2 to pi? Well, that's the same as saying theta is going from pi over 6 to pi over 3. And as 3 theta goes from pi over 2 to pi, cosine of 3 theta goes from 0 to minus 1. So when you add 1 to that, you go from 1 to 0 as your angle sweeps up to here. So as your angle goes from pi over 6 to pi over 3, or 2 pi over 6, your distance from the origin drops from 1 down to 0. So now you come in here and drop down to 0. Trying to smooth that out. Drop down to 0. Then what happens? Well, you can look at it as your angle goes. So that was as we went. So here's pi over 6. That was as we went from here to pi over 6. So maybe I need to draw this as sweeping in more. So as your angle went from here to here, but now as your angle goes from, well, we'd also like to see what happens as 3 theta goes from pi to 3 pi over 2. But that's as theta goes from pi over 3 to 2 pi. Well, what happens? Well, cosine of 3 theta, as 3 theta goes from pi to 3 pi over 2, cosine of 3 theta goes from minus 1 to 0. So this goes from 0 back out to 1 as your angle increases from here to here. So you go back out to a distance of 1 from the origin as your angle sweeps from here to here. Okay. Then when you go another pi over 3, you'll go back out to 2. You can finish this. But what happens is you'll go back out to 2. As you go another pi over 3. Well, let me just go ahead and finish this. You can do this. But what happens is these close. So right. You get this. It's normally referred to as a three-leafed rose. It has these three petals in it, and that one's not quite right. Anyway, it has these three petals in it. You could draw it better than this. I'm trying to do it quickly, but yeah, as theta goes all the way around, you keep coming in and going back out to the origin, and yeah, you get this three-leafed rose. It's kind of cool. A lot of calculators and computer programs will draw polar curves for you. Anyway, I just wanted to give you an idea of how you draw those qualitatively. You just look at nice increments in the theta and just look at what r and theta do. But as far as calculating the area of it, you need to know what thetas give you the whole thing. Now, by symmetry, you can probably say, oh, yeah, the integral is 6 times, the area is 6 times whatever half the area of one of these leaves is. Oh, I should say, there's something, there are other three-leaved roses. And in fact, this isn't the most common one. Most people would use r is 2 cosine of 3 theta. That actually has a different area. It's this three-leafed rose is inside of this one. It has smaller area. So this is the one that most people, or something like this is what most people mean when they say a three-leaved rose. I'm just trying to give you the general, kind of describe the general shape. All right, but how do you find the area of it? Well, you just need to know that you get the whole thing as theta goes from 0 to 2 pi. And then you just calculate the area. We could do 6 times the area from 0 to, we got this top half. We could do 6 times the area as theta goes from 0 to pi over 3. Or we can just do the whole 0 to pi over 2. It doesn't really matter. So I'll do the whole 0, to 2 pi, not pi over 2. 0 to 2 pi. And then it's just 1 plus the cosine of 3 theta squared. All right, so you have to do this integral. Actually, you do this integral the way we did the last integral. It's just got a 3 theta in it. You'll get 1/2, and then the integral from 0 to 2 pi. You square it, you get a 1 plus 2 cosine of 3 theta. Plus a cosine squared of 3 theta. Use the same trig identity we just used. So you get 2 cosine of 3 theta. And then by the trig identity, this is 1 plus, before we had 2 theta, but that was when we had a theta in here. Now it's 2 times 3 theta. So you get the cosine of 6 theta over 2 d theta, and you integrate, and you get the answer. So let's just do it to finish the problem, but at this point, it's just a couple of easy substitutions. U equals 3 theta and U equals 6 theta, but I can do those on the fly. So what you get is theta plus 2 times the integral of cosine of 3 theta plus 2 times. You get the sine of 3 theta, but then after you fix the substitution, it'll be divided by 3. Actually, it's easy to verify that by differentiating. If you differentiate this, right, we're finding antiderivatives. So if we differentiate this, we should get what we had a minute ago. But yeah, when you differentiate, a 3 will come out by the chain rule, cancel this 3, and yeah, you'll get 2 cosine of 3 theta. Then we get plus 1/2 times, then there's a theta, and then plus the sine of 6 theta over 6. Again, you can make the substitution, U equals 6 theta, but if you differentiate this, you'll see that you get the cosine of 6 theta, because the chain rule will give you a 6, and it'll cancel with that one. And I've got the half way out here. So we do this and evaluate from 0 to 2 pi and try not to make any mistakes, although I make them all the time myself. When theta is 2 pi, we get 2 pi. This is 0. We get a half plus a half times 2 pi. This is 0. When you subtract what you get at 0, we get 0 again. So we get 3 pi times half. We get 3 pi over 2 for the area, which strangely is what we got a minute ago with 1 plus the cosine of theta. It is certainly not true that all integrals of polar function, you take r equals f of theta, the answer is always 3 pi over 2 for the area. No, it's not. It's just a fluke. Although it could be true, and you might want to do this as an exercise, that if you take r equals 1 plus cosine of k theta, where k is anything, that what you get is 3 pi over 2. Let's see, is that true? Could be. Could be. Sounds true. Can I do that in my head quickly? Yes, I think, yeah, that should be true, because all these places where we have like 3 theta, we'd have a k theta, and a k theta, and it'd be divided by k, and it'd be, or 2k, and it'd be divided by k. Yeah, that should be true, but I'll let you do that as an exercise. Anyway, this is all I wanted to do on area swept out and area in polar coordinates. It's an interesting kind of cool topic. It doesn't come up, the area swept out doesn't come up that often. Area in polar coordinates is nice to know. It doesn't come up so often, but some regions are just nice in polar coordinates, and you can see you get lots of symmetries and lots of cool pictures, so it's certainly beautiful. Useful? We'll see.